Hi, I'm Yoni Eldar. I'm the head of the sample lab at the Technion, and what we're presenting here today is work that we've been doing for several years in our lab, where we've been developing both the theory, the algorithms, and prototypes for Sub-Nyquist sampling. So the idea is that we could take many different types of signals and sample them and process them at rates that are much lower than the Nyquist rate. So we've been working on developing the theory and algorithms for that for several years, and what we're doing here is actually building prototypes and showing the advantage of this Sub-Nyquist sampling in a variety of different applications. So one application is in radar, where we show, and we'll go into the demos later on, now I'm just giving an overview. So in radar we can show that we can detect we can detect targets at using samples at rates that are much lower than the Nyquist rate. We get the same resolution as you would as if you were using the high Nyquist rate. We could then exploit that to do cognitive radar, where basically we could recover the different targets that we're looking for using several narrowband signals for transmission instead of a very wideband signal, and that enables us to coexist with wireless channels. And finally, we could reduce the time on target that we need in order to identify the target, and that allows us to sweep a very wide area, whereas an existing radar would only be able to sweep one angle. So that's that demo that Shachar will show us later on in more detail. The next demo is ultra-wideband communication. So we know that there's many advantages to ultra-wideband, for example, in terms of diversity, but one of the big problems is the sampling rate that it requires at the receiver. And what we've developed here is an ultra-wideband system where we could both identify the channel, do channel estimation, and symbol detection at rates that are much lower than the Nyquist rate. So that's the second demo that Shachar will be showing us. And the final prototype that we've developed is for cognitive radio. So the idea in cognitive radio is that if we're able to scan a very wide spectrum, we could find where there's white spaces, where there's white holes, and let secondary users on the channel. But that spectrum sensing problem is very difficult in practice because there's a very wide spectrum to sense. What we've developed here is actually a prototype of a cognitive radio system where we could sense 3 gigahertz wide spectrum at very low rates. So our total rate is only 6% of that, so about 250 or so megahertz. And we're still able to not only detect where the transmissions are coming from, but actually detect the symbols in that transmission as well. So that's this prototype over here that could sense a very wide spectrum at very low sampling rates and very low processing rates. So that's an overview of the system we're showing here, and now I'll turn the floor over to Shachar to actually show us each one of these demos.
Hi, my name is Shachar. I'm part of Yoni Eldar's lab at the Technion, and the systems here, the Sub-Nyquist systems, are systems we've developed together with National Instruments, and I'll be happy to show you them. The first system is the Sub-Nyquist cognitive radar. What we're able to see here is a radar input being generated and inserted into an analog front end. This is the analog front end that takes slices out of the spectrum of the radar and allows us to work in subsamples. The targets are being generated here, they're being added with clutter and noise and summed up. The entire scenario is being generated and then sampled at just a fraction of the original samples that would have taken us originally. We are still able to fully detect the targets in the range Doppler map. Another part of the radar is the cognitive radar. Let's say we know the spectrum, we know what's taken and what's not. We can actually use the vacant spots and transmit on them the radar pulses and achieve better SNR and better performance. And that's what we do here. The red frequency bands, those are the bands we transmit on. And we achieve much better results than the actual Nyquist sampling that would have taken the entire spectrum, because we achieve better performance both in energy in each slice and in precision in each frequency slice, while maintaining a very big aperture in frequency domain. The targets here are also shown to be fully recovered and reconstructed. Okay, so if we are able to sparsify in time and take Fourier samples, why not try to get 2 directions at the same time? And that's what this demo does. It's called reduced time on target. It allows us to transmit in 2 directions or more, in this case only 2, and fully detect the targets in each one in parallel. We can see the targets here at the top and both at the bottom that depict 2 different angles are being acquired and located at the same time in high precision. The accuracy is very high, over tens of kilometers, we get precision of just several meters. Moving on to the ultra-wideband, this system knows how to perform a full channel estimation of an ultra-wideband scenario with a very high compression ratio. In this case, we compress by a factor of 2. We can also compress by a factor of 4 and factor of 8, and fully detect the QPSK constellation that is seen here. Our results, our EVM results, are comparable to the Nyquist rate and allows us to estimate the channel fast and accurately. Okay, now to the final system we have demonstrated here. That's the Sub-Nyquist cognitive radio system. We have the transmitters being implemented on the USRPs and inserted into the MWC. This analog front end allows the signal, allows all of the spectrum that is spanning between 0 and 3 gig, allows all of it to a very narrow bandwidth of just 60 megahertz. That's the baseband. So we go down from 3 gig of possible information to just 60 megahertz. The entire range of frequency domain contains just a few sparse number of transmissions on it. We don't know the original position, so originally we would have had to sample at the Nyquist rate of 6 gig, twice the maximum frequency. Now, because we have the MWC that allows everything to the baseband, we're able to decompose and recover the support, the actual frequencies that are transmitted. Everything is happening in real time, and after recovering the frequencies, we are able to fully reconstruct the signal in the digital domain. So we can see at the top, that's Nyquist sampling, the traditional Nyquist sampling. Here at the right, those are the Sub-Nyquist samples that we sample over 3 channels. And at the bottom, that's the digital reconstruction, a perfect reconstruction in which we didn't lose anything, only gained a much better scenario and much better sampling rate and performance. As I just said, the cognitive radio allows us both to recover the frequency support and the information on the bands. So what we can see here is we're inserting special strings on each channel. In this case, NA demo, sample lab, and this is channel 3. Just any strings we want, any information we want, we can modulate and put on the bands. And what we can see here is happening in real time. We can actually detect the frequencies, detect the support of the signal, and fully reconstruct the data. That's QPSK constellations, and those are the strings recovered from the Sub-Nyquist samples. Okay, remember those are Sub-Nyquist samples that we sample at a very low rate. Okay, so those are the capabilities of the cognitive radio. I hope you're thrilled about the system as much as I do, and thank you very much.